Right, here is a practical looking at the inverse square law for gamma. For gamma radiation, that is. Okay, so we should have a pretty good idea that this gamma source that we have will be shining out radiation. And as the radiation increases with distance, so the intensity of that radiation diminishes from an initial value. And it behaves according to a simple law, which is the intensity is going to be the original intensity divided by 4 pi r squared, r being the distance between the detector and, let me draw that a little further, and the source. So what do we need to explain with that? Well, I suppose the rationale there is that we have a little area which this radiation is passing through. And as it goes further, so this area increases. And the intensity, of course, is that around the entire sphere. So it's an inverse square law. If you want more information, turn to another video. I'll put in the link below. Good. Now, this is a Geiger counter. And a Geiger counter, we get a little number that's shown on this. And that's worried. That's going to give a count if this radiation, this gamma radiation, ionizes the gas which is inside the Geiger Müller tube. Of course, the sensor is there. We are taking measurements from the end of the Geiger counter. So in all cases, we do have this systematic error that we call, let's call it X. So little systematic error to all of our readings we'll call X. Okay, so this therefore has got to be rewritten. What we ought to be saying is that the intensity is going to equal the initial intensity divided by 4 pi r plus x all squared. And whereas we might have, in order to prove this law, we might have drawn a graph of intensity against 1 over r squared to get a straight line and prove that relationship. That will not happen here because we have this correction factor built into the results. So therefore, let's do a little bit of rearranging of this equation. I'm going to move these two around, and I'm also going to, it's probably worth saying here, the count rate which the detector records is not actually strictly the intensity. The count rate is the number of ionizations that occur in here. But what we do know is that if the gamma ray has a greater intensity, the count rate will increase. So what we can say is, we can say that the intensity is directly proportional to the count rate. So therefore, let's rewrite the equation as the count rate is going to be the initial count rate over 4 pi r plus x all squared. Let me move this around by moving that up. So that's going to give me C naught over 4 pi, 1 over the count rate, gives me r plus x all squared. I'll remove the squares, so that gives me r plus x is the square root of a constant by 1 over the square root of the count rate. And therefore, finally, the way I'm going to do it, we're going to say r is equal to square root of this, let's just call it a great big constant. In actual fact, we can just call it a constant. Hold on, this makes life easier. a great big constant by 1 over the square root of count rate minus x. Good, so when we do our graph, what I need to graph is r against 1 over the square root of the count rate, and what I should get is a straight line with a negative intercept of x. So I can work out the intercept, the end correction by working out the intercept. Okay, now there's different ways we can rearrange this. If we wanted to, we could rearrange it in such a way that we plotted 1 over the root of the count rate there against distance r, which might be better because you can say that this is your independent variable. You're going to change positions, and this, of course, is your dependent variable, so that's how it ought to be plotted. Better. But that would mean then here we're going to have to rewrite this equation as r plus x divided by this great big constant is 1 over the root of the count rate. So therefore, if I plot r, so therefore if I plot, let's do this y equals mx plus c just to work out y, mx plus c, just to bear that in mind. If I plotted 1 over the count rate like I have there, let's jump straight to here, I would probably get a line that did that, in which the intercept here would be x over this constant. And you could work out that constant because the gradient here would be equal to 1 over that constant. Or indeed, we could track this back and look for the intercept there, and that would give us x. So there are multiple ways of doing it. I'm probably going to do it this way, but this way is just as valid to intercept that. I'm going to collect the results, show you how to collect results. You can interpret it and draw the graph however you want. Okay, let me show you the experimental setup. Okay, here's the experiment that we've got. I've got a Geiger counter sitting here. I will have my source mounted in there. Note the gloves because I'm using radioactive sources. I will have my source mounted there, and here is the Geiger probe, which will be taking readings of how much radiation, gamma radiation, is being received at these varying distances here. First of all, I need to turn on, obviously, the Geiger counter because I need a background count, first of all. So if I start, I'll turn on the speaker in the first instance so you can hear the noise of the background count. And then what's important is if I take that count over a given time. So I think what's probably a good idea is if we take that count over a minute, let's say. So we're looking for, just move that a little bit out of the way. So we're going to look for, in terms of results, for the background, we're going to look for the counts per minute. Once, twice, 3 times, and then an average. Because you know that this isn't going to be a stable number. It's going to vary. Good, that's the first thing we're going to do. And then, from there, what we need to do is build up our table of results. We're going to be looking for, first of all, the distance here is our independent variable. Let's just write in distance in meters. We're then going to be measuring the count rate, which is our dependent variable per minute. once, twice, 3 times, and an average. We probably then want a corrected count rate per minute, because we want to take the background count off of that. And then we're looking to get 1 over the square root of the count rate. And that will be minutes to the minus a half. So that, in effect, is our table. In which we're going to gather our data from. Right, so make sure you have a stopwatch as well available. I've got one on my computer here, which I'm using. And we want to take the counts per minute, reset, start, and then slowly fill in my values for that. Excellent, right, here comes the source. There is my gamma source, cobalt 60, gamma producer, and I'm wearing gloves, of course. It comes in a lead shielded box. And inside there, so I take out with tweezers. I'm using long plier tweezers because then, in most instances, that's a big enough distance for radiation not to get to my hand. This is a gamma source, of course, so there is plenty of radiation to penetrate that distance, but luckily it's not very ionizing. Okay, take this off, mount that, and set it up. Move the box away. Okay, make sure that you're shining it away from you. Make sure it is aimed at the Geiger counter, of course. And you'll probably hear, if I turn the speaker back on, we've got many more counts going on. So this will be at 16 centimeters. So for our position of 16, we're going to look at the count. It takes for 1 minute. Then we will reset that and the stopwatch. And then look for another minute. And the same again. Reset the stopwatch again and look for the average. Just like we did for the background count. Then we move this into a new position, which is closer. And you'll note the increase in the count rate. Reset it again, reset the stopwatch, take a count, etc., etc. That's, let's take the speaker off now. It's a fairly safe setup there, making sure that that's shining away, you're a good distance away from it, and you've got your Geiger counter ticking away with the numbers. Okay, I have taken all these results before, so I'm going to show them to you so you can then interpret and draw that graph. Okay, here are the results. The varying distances, I've taken the count rates averaged out, the corrected count rate, because we have a background count of 15, and therefore 1 over the count rate minutes to the minus a half. Good, and then you just have to plot them. I mean, I suppose it's worth saying here that the background, what I did was I discovered it's 15, 18, 12, which gave me an average of 15. I've placed that just there. It's important that you do that. And then with that data, so you can hit pause and copy it down, but there's also a link lower down in the video. But then with that data, remember what we're going to do is we either plot R against 1 over the root of the count rate, and we will get this point here being X, or we plot R over 1 over root count rate, and we get that the intercept there being X. Either way, we can work out what that correction is between detector and the end of the Geiger-Müller tube. Okay, good luck with plotting that, and I hope it comes out with the right results.